Welcome back. So today we are going to be doing our last lesson in the gas unit, and that is on the ideal gas law. So what we have, of course, where we do have the ideal gas law, we had to figure out what an ideal gas is. So an ideal gas is just a hypothetical gas. That obeys all the laws perfectly under all conditions. So the reason it's hypothetical is they don't really exist. However, we will kind of need to imagine hypothetical gas in order for the equations to work out. So what a hypothetical gas means is that the size of the ideal gas is negligible. So basically, like, we assume that they almost have no size whatsoever. There are no forces of attraction, meaning that there's no intramolecular forces. So that means that they do not condense when they're cooled. All right. Now we know this isn't going to be the case because a real gas is an actual gas that condenses when it cools, and it can deviate from the ideal gas law under certain conditions. Now these are going to deviate under extremely high pressures and extremely low temperatures. So for relatively low pressures and high temperatures, though, like STP and SATP conditions, real gases do behave like ideal gases. So this is why we're going to be able to use the ideal gas law. Now, if you study chemistry more, like at a university level, you'll start learning how to do deviations away from the ideal gas law. But just right now, we're just going to say, all right, the ideal gas law, all gases are going to obey it. So what we have is the explanation of our equation is that we need to basically look at all of our relationships. So Boyle's law, Charles' law, and even Avogadro's theory. So we knew Boyle's law, we had an inverse relationship between pressure and volume. So what this inverse relationship meant was volume was related, so in math we use this, or proportional, it was inversely related to 1 over P. So that meant that as P increased, or as volume increased, pressure went down, or as volume decreased, pressure went up. So that's the inverse relationship. Charles' law had the direct relationship between volume and temperature. So volume was directly related to temperature. So if volume went up, temperature went up. If volume went down, temperature went down. And Avogadro's theory, we just talked about a little bit, but this was a direct relationship between, in this case right here, volume and number of moles. And that is, of course, as if we put more gas inside of a container, the volume went up. If we took gas out of the container, volume went down. You can imagine like blowing into a balloon, this type of thing. And that was kind of brought into molar volumes as well. I know we kind of fixed on, it was different, but that was kind of that relationship that Avogadro kind of went with. So you'll notice here that all of our relationships that we've done, Boyle's law, Charles' law, and Avogadro's, volume was in all of them. And we can kind of combine all these together. You notice that volume is proportional to 1 over P. It's also proportional to temperature. It's also proportional to number of moles. So our ideal gas law is going to combine all of these variables right here. So volume, pressure, temperature, and number of moles, because the volume of a particular gas is dependent on all these things. So our ideal gas law is PV is equal to nRT. Now, first thing you're going to notice, like, oh, I haven't seen R before, and that is true. So in order to get rid of those proportional signs, they used an R constant, which is the universal gas constant. So this was theoretically or mathematically proven, so it makes this equation true, right? So that's when we go away from, okay, it's not proportional anymore, it's actually equal to something. So our ideal gas law, or our gas constant, is 8.314 kilopascals, liters times kilopascals over moles times Kelvin. So that means that when we look down here, pressure needs to be in kilopascals, volume needs to be in liters, the chemical amount needs to be in moles, and the temperature needs to be in kelvins. And that is because, when we talked about it before, is that when we're putting something inside of the equation, we need to make sure that the units match. So because the universal gas constant, and this value is found on the back of your periodic table, so just make sure you can find it. So the units here is kind of driving everything that we have. So that's going to be the big thing, is of course writing down all of our givens and making sure that the units match up. So I'm going to go over example 1 and probably example 2 and let you guys work on 3 and 4, and then of course you can do your CYU book. So example 1, we have a weather balloon has a capacity of 10,000.0 liters at 100.0 kilopascals and 20.0 degrees Celsius. So how many moles of hydrogen must be generated to fill this balloon? All right, so let's write down all of our givens. So we have our volume is equal to 10,000.0 liters. Pressure is 100.0 kilopascals. Temperature is 20.0 degrees Celsius. Right, but remember we had to convert that into kilopascals by adding 273, so we get 293.0 Kelvin. R is always a given, 8.314 liters kilopascals over moles Kelvin, and N is equal to, we don't know. So you'll notice that I'm writing down all of the units here as well, because I need to have a quick little scan, look at my R value right here, and make sure that all the units match up. So in my R value I see liters, in my volume I see liters. Okay, so they match up. I see the pressure unit is kPa, kilopascals. I see my pressure in kilopascals. Good. Chemical amount, N, well that's what we're going to solve for. And finally degrees Kelvin, and we can see Kelvin right here. So all my units match up, perfect. So now I can actually write my equation. So PV is equal to nRT, and solve. So of course, rearranging this equation, we will notice that we are solving for N, which is right here, and N is being multiplied by both R and T. So when we're trying to isolate, we end up having to divide both sides by R and T to get them to cancel out. So with N is equal to PV over RT. And of course I already looked at all my units, so I know my units are fine, so I can just go right ahead and plug all these values in. So my pressure is 100.0 kPa. My volume is 10,000.0 liters over R, 8.314 liters kPa over moles Kelvin. And finally, my temperature is 293.0 Kelvin. And N is equal to 411 moles. So this is rounding with 3 significant digits, because our 20.0 had the lowest number of significant digits, and that was 3, right? Now, just like when we did the other gas law, or the law of combining volumes, the molar volumes, we use number of moles, or solve for number of moles for mass. So this is going to be similar. We can have a two-step question, which is example 2 right here, when we're given a mass. All right, so in this case right here, we will kind of need to do 2 steps in order to solve. But as long as you know which equations to kind of use and which ones to plug in, you're going to be fine. All right. So just make sure when you are writing these here, so write everything down. So a natural gas storage tank contains 2.65 kilograms of methane, and methane is CH4. Contains methane gas at 600 kilopascals and 18 degrees Celsius. What volume is this storage tank? So, of course, right here we have to write out all of our givens and then, of course, solve. All right, so our givens in this case right here, we are given a mass of mass is equal to 2.65 kilograms. Now, right away, kind of recognize that at no point have we ever really used kilograms before. And then, of course, if we're given a mass, we will need to know molar mass for CH4, which the molar mass for methane is 16.05 grams per mole. And so because where we see the units of grams inside of our molar mass, we should convert kilograms to grams, which we multiply by 1,000. And we get 2,650 grams. So that's those. Now we have P is equal to 600.0 kPa. Temperature is 18.0 degrees Celsius, which we're going to convert that into Kelvin by adding 273, and we get 291 Kelvin. R is equal to 8.314 liters kilopascals over moles Kelvin. And that is basically all of our information from the question. Now we will notice we will need to use the ideal gas law, PV equals nRT, and we don't have N. Now N is going to be hiding, or the number of moles is hiding within, of course, our mass. So our first step, before we can use our equation, we need to find number moles. So number moles, just mass divided by molar mass. So we take our mass of 2,650 grams divided by the molar mass of 16.05 grams per mole. And we're left with number of moles is equal to 165.109 moles. That's fine. And of course, our second step, so PV is equal to nRT, and we're solving for volume. Now in this case right here, we are isolating for V, right? So in order to isolate for V, we have to divide both sides by pressure. And we're left with V is equal to nRT all over P. So V is equal to number of moles we just solved for. R is 8.314. I'm going to leave the units out here just because I'm a little tight on space. And all over pressure. Alright, so this is what we have. Now I'm going to write that up here. So volume, what we end up getting is 665.77 liters. Now this is my unrounded. I do need to round finally, so I look at all of my givens. I see 3 significant digits here in the mass. I see 3 significant digits in the temperature. That's my lowest number, so we end up getting 666 liters. So the volume is 666 liters. All right, now there's 2 more questions on the next page, and these are the last 2, and of course you guys can work on your CYU books. But just having a quick look at these right here, pause the video and try them out, and I'll put the answers up now in 3 seconds. Alright, so the answer to example 3 looks something like this. So you should get a mass of 4.50 grams in the workings right here. So if you want to just pause the video and kind of go through, make sure everything matches up, please do. And finally, the last one, example 4, you should get negative 26.8 degrees Celsius. And of course, the workings right there as well for you to see. Alright, so that is completely it for the gas unit. Your next little thing is you're going to be working on a gas law assignment, and that'll be your next week stuff. So there will be no new lessons for next week. And then we're going to jump right into solutions after that. So I'll see you guys later.